Alrighty, so my paper was efficient CapsNet, Capsule network with self-attention routing. A little breakdown of the paper. Intro related, it goes into the intro, covers some related work, methods that they use, their results, and then finish off with their conclusion. It was written by these folks here in Italy, and starts off with, then we have their abstract right here, talks about like, they talk about methods that they use already to solve the problem that they're trying to solve. Talk about how some of the things they're using were developed, and and then give a little summary of the results. So yeah, in the introduction, they talk about how reconstruction and image classification is being handled right now. They break down how it's being handled right now. They have a diagram. This is a diagram for CNN. And then they talk about this idea that this guy, Jeffrey Hinton, had. Now, I know who Jeffrey Hinton is. I've seen him in Andrew Yang's deep learning course. And I know he's like a father of deep learning and everything. But I'd never heard of this capsule network idea, so that was his idea. And then they talk about how they want to use the attention mechanism for routing. This capsule network thing was also around, and it used a different kind of routing. So they go, and then they want to cover three things that they go into: deep investigation of generalization of this thing, these things that they're trying to implement, integrating self-attention and getting state-of-the-art results, and then the highly parallelizable, non-iterative, again, self-attention idea. Some of the related work, again, the Jeffrey Hinton came up with this CapsNet, and the whole idea of this capsule. This Zai gentleman also worked on CapsNet. But at the end here, they have a diagram of what they're determining to implement. And so you have just a regular CNN. In the beginning here, you have this would be like an image, the input tensor, then CNN, and then depthwise CNN, and then here you have the attention layer, which helps route these capsules here, which they explain down here, the EfficientNet, and then they explain the capsules. The capsules are like, so within the CNN here, you have the regular activation layers, but capsules are sort of like vector versions of the activation weights and activation layer. So you have a higher expressibility within the attention layers. And they cover this is how it's handled in the CNN, the relative function, but they want to use this squash idea, which makes things much more useful. Much more things that are closer to zero will be more impactful to the system with this squash function instead of just the relative function, where it just completely wipes it away if it's relatively close to zero or whatever threshold you pick. And then they use the self-attention routing. So the self-attention block diagram up there. This is a breakdown of that. You have the capsules here, which here they have the previous capsule tensor or matrix, and then they have the current capsule matrix, and they use self-attention in this matrix form or tensor form, and they take the dot product, sort of like the queries and keys, and divide by the key dimension. Then they have this attention tensor, so it's like a much more complicated version of the regular attention mechanism, and they put it through this softmax function and exaggerate and scale the between 1 and 0 the attention values, and then they use L2 loss. Then their results, they use these three data sets: MNIST, small norb, and small norb, and multi-MNIST. Their settings that they use, the efficient CapsNet, and then they go into a little reconstruction comparison here. Now, this is efficient CapsNet, and then CapsNet with self-attention, and then their competitors, and then the ground truth. And you see that these are kind of the same, but then these all look the same. It's like this is doing pretty much the same as this, and this is doing pretty much the same as this with them. But you got to remember, this is doing much better than with the old routing, but or not much better, but it's with less parameters, like 1/10 of the parameters, and it's still getting the same results. Then they use RTX GPUs, Q11. Then their MNIST results and their small norb results, they tabulate here. Here's your efficient CapsNet, 161,000 parameters with 0.26% loss versus, I mean, it's like half of all the other competitors. And where it isn't half for some of the competitors, again, it's like 1/10. This is a 60th of and 1/10 of the parameters. Then they're trying to push their state-of-the-art claim here. 2021, they're keeping right up with this previous base branching method with 0.16% test error. And then the norb results, the small norb, the other one was the MNIST, this is the small norb results. Again, you have the efficient CapsNet, 151 thousand parameters, and 2% loss, and half the loss of, again, the competitors. And where it's not, it's 1/3 of the parameters, which we're talking about hundreds of thousands of parameters. And then they use this multi-MNIST result data set to benchmark their results. So the multi-MNIST data set is a data set with two images superimpose, and they just use that merged superimposed image as the whole input. So they make one image out of two images by putting them on top of each other. And so this, there's no metric to measure it, but the machine, their system, the efficient CapsNet, thinks this is about 4 or 9, which with our eyes, I mean, just by looking at it, it's about right. And the green bars represent correct labels and their high corresponding capsule length. But here you see it looks kind of like a 4 or maybe a 6. Someone really, that's pretty good. I mean, I would think the same thing. And then this is probably a 0 or maybe a 2 or maybe a 8. Could be an 8. And again, like that could be a 5 or a 3 or a 7 or a 2, you know. So pretty compelling. Then this is another, so this is like the relative usefulness, like just from your site, but then you put these reconstructions against the competitors, Efficient CapsNet. These all look the same, but you got to remember this is with 1/10 of the parameters, with this CNN and this CapsNet with dynamic routing. It's keeping up with all the, way better than the dynamic routing. It's keeping up with all these guys with 1/10 of the parameters. And then they want to explore the affine transformation embedding, which they say they just tweak the input a little bit and then look at the output, see how it affects the output, and they're able to gauge like the origin and like the position of all the pixels with this covariance matrix. And yeah, they don't label their axes here, but within like 2 iterations, they're pretty much already spot on with a little tweak, -5 to +5 tweak in the X domain and a little tweak in the Y domain. And then same thing with rotations, a little rotation in the system in the input, and it's pretty much guessing correctly within the second iteration. And then random heavily affects the system, which I'm guessing will affect, they don't have any comparisons for other systems, but it's only one, it's not a multi-trend graph, so yeah, I'm guessing it would affect any system, right? Machine learning, random, if it's good random set. Then they come up with this eigenvalue ratio metric, and yeah, then they tabulate the results here. And yeah, again, random had a heavy effect on the system, and their conclusion is this it holds merit. It proves that this system could have high generalization potential, and they want to work on that in the future. And like I said, that's their conclusion. And then they go to the numbers. Like I said, this is a high level. I mean, I tried to get it done in 5 minutes, but it was 10 minutes. I went as fast as I could. And this is super high level. Like the whole capsule idea is like a huge system all in itself. And like I said, my name's Norman Sabin. And if you want to like talk about like the whole capsule idea, or like talk about this paper, or like what you think or whatever, like I said, my email is Sabin, my last name,